One more important concept in inductance is mutual and self-inductance. In our previous chapter, we studied the magnetic interactions between two wires carrying steady currents. So the current in one wire causes a magnetic field, and that magnetic field exerts a force on the current in the second wire. So, but an additional interaction arises between two circuits when there is a changing current in one of the circuits. So here we have two neighboring coils of wire. Current in coil 1 produces a magnetic field and also a magnetic flux, and this magnetic flux is passing through coil 2. If the current in coil 1 changes, the flux through coil 2 also changes. So according to Faraday law, the change in current in coil 1 induces an EMF in coil 2. So a change in the current in one circuit can induce a current in second circuit. The magnetic flux, so in this figure, a current I1 in coil 1 sets up a magnetic field, and some of these magnetic field lines are passing through the coil 2, and this one is represented by phi B2, which is the magnetic flux caused by coil 1. Okay, if the flux is different through different turns of the coil, then we will take the average flux phi B2. Okay, and magnetic flux is proportional to I1, so phi V2 is also proportional to I1. When I1 changes, the current in coil 1 changes, magnetic flux in coil 2 also changes. So the changing flux induces an EMF in coil 2, and this is written as E2 phi B, and in coil 2. So there is the flux is proportional to the flux phi B2, and current I1 are proportional to each other. So we can write phi B2 is proportional to I1, and it is more convenient if we also include the number of turns in coil 2. So this phi B2 becomes phi becomes I, and N2, the number of turns in coil 2. And so we can use a proportionality constant here, and that proportionality constant is represented as M21 I1. This we introduce this proportionality constant, and this is called as mutual inductance of two coils. Here phi B2 is the flux through a single turn of coil 2, and we can write N2 d phi B2 over dt is equal to M21 di over dt, and so this equation can be used here, and we can write induced EMF is equal to minus M21 di over dt. So the change in the current uh, I1 in coil 1 induces an EMF in coil 2 that is directly proportional to the rate of change of I1. And we can also write the definition of mutual inductance as M21 is equal to N25B2 over I1. If the coils are in vacuum, then the flux through coil 2 is directly proportional to the current I1. And the mutual inductance is a constant that depends on the geometry of the two coils. So the shape, size, number of turns and orientation of each coil and the separation between the coils. If a magnetic material is present, then this M21 also depends on the magnetic properties of the material. For example, if the material has non-linear magnetic properties, that is if the relative permeability is not constant and magnetization is not proportional to magnetic field, then this phi B2 is no longer directly proportional to I1. In that case, the mutual inductance also depend on the value of I1. And we assume that any magnetic material present has constant Km, so that the flux is directly proportional to the current, and M21 still depends on geometry only. And now we can also use the same calculations for the opposite case, in which a changing current I2 in coil 2 causes a changing flux phi B1 and an EMF E1 in coil 1. And we may expect that the corresponding M12 would be different from this M21, because in general the two coils are not identical and the flux through them is not the same. But it turns out that M12 is equal to M21 even when the two coils are not symmetric. So this common value is called simply the mutual inductance, and we represent this one without subscripts. We represent it with M, and it characterizes completely the induced EMF interaction of two coils. So we can write it for E2, it becomes di over dt I1, and for E1, the opposite case where the EMF is induced due to coil 2, and we can also write this one in the in this form, basically. So mutual inductance for was N2 phi B2 over I1, and with this simplification we can write N2 phi B2 over I1 is equal to N1 phi B1 over I2. This is mutual inductance. And when a negative sign came, then it will come, it means that it represents it's a reflection of Lenz's law, and the unit of inductance is Henry. It is 1 Weber per ampere, or we can also represent it in the form of Joule per ampere square. There are also some drawbacks of mutual inductance, because it sometime in the circuit it induce unwanted EMF in other nearby circuits, and it has also some useful applications. For example, a transformer used in an AC circuits to raise or lower voltages is a realization of mutual inductance. Then there is